Hello and welcome to our second special topic, direct current transmission technologies. I'm Adam Reed from the Renewable and Sustainable Energy Institute in Boulder, Colorado, USA. In this webinar, we'll discuss some recent developments in direct current or DC transmission technologies that may play a substantial role in the future of large-scale renewable energy. Thinking about transmission as an integration tool can seem counterintuitive because we normally think about transmission as the space in which integration occurs and not a part of the process itself. But transmission expansion is a big part of integrating renewable energy for a couple of reasons. First, and most obviously, new transmission can connect remotely located renewable energy sources to the rest of the grid and ultimately to loads. Without it, there's nothing to integrate in the first place. For many renewable energy plants, the cost of new transmission is one of the biggest components of integration costs. Second, new transmission, not even directly related to a new renewable energy plant, can provide greater interconnectivity to a grid, particularly if it connects two parts of the grid that had previously only balanced generation and load within their own respective territories, or even two grids in two different countries. In other words, transmission can also introduce more systematic diversity to the grid, which can result in a net reduction in system variability and lower overall costs over time. Third, larger and more interconnected grids have better access to all the sources of flexibility that we've discussed in the preceding webinars, whether it's faster ramping conventional generation, energy storage, advanced wind turbine capabilities, demand response, or access to better control room and weather forecasting technology. Larger grids with more resources and more loads are better positioned to integrate renewable energy in a cost-effective manner. Moreover, a larger grid simply has more available line capacity to absorb and distribute unscheduled flows from wind farms, solar plants, and related integration activities. One of the emerging technologies that's making a big impact on the interconnection of electricity grids is a return of direct current transmission, and we'll talk about those new technologies here. But to best understand what direct current is and what it means for the future, we have to go back in time, over 100 years ago. In the late 1800s, a debate raged between the direct current-based electricity systems of Thomas Edison and a young upstart named Nikola Tesla, who promoted a system based on AC power. The story is worth recounting here, as it not only teaches us a lot about AC versus DC power, but is also a fascinating account at the heart of the advent of the modern age. Thomas Edison, famous worldwide for his electric light systems, based his systems off of steam engines, which burned coal, wood, or oil to boil water and turn a turbine, which was connected to a generator, simplified in this illustration into a rotating armature surrounded by a magnet. The generators, by design, created direct current power. DC power moves in a single direction through the system, just like a battery, due to the split ring design of the commutator. Edison's systems were wildly popular, and he built hundreds of them around the world. But he was limited by tremendous loss of power over transmission distances of more than a few kilometers. According to Joule's law, the power loss in the system was equivalent to the resistance of the wire times the current squared. The upshot of the equation is that losses increase exponentially with higher currents. This limited the reach of Edison's system to within 2 kilometers of the power plant. There's a workaround to this problem, however. Ohm's law tells us that voltage equals current times resistance. If we restate that, we can also say that resistance equals voltage divided by current. If we substitute that new value for resistance back into Joule's law, we learn that power equals current times voltage. That means that we can reduce the current to minimize line losses, but still transmit the same amount of power if we increase the voltage. This also had a problem, though. High voltage is extremely dangerous, and it already killed a number of people around the advent of the electric power system. Enter Nikola Tesla, Serbian inventor who immigrated to the United States in 1884. Tesla, who would patent a number of alternating current generators over the course of his career, found a way to use high voltage for long-distance transmission without the attendant safety risks, and advocated building an entire power grid around AC. Why? Because alternating current, unlike direct current, continuously alternates the direction of electrical flow within the wire, surging back and forth rapidly. This is due to the design of the generator, which uses 2 slip rings, one for each end of the rotating armature, rather than a single split ring like the one we saw in the DC generator. This surging of current back and forth through the line creates electromagnetic radiation that can induce current in nearby but unconnected conductors. Tesla designed the device that worked off of this principle and allowed for easy voltage conversion, called a transformer, which he patented in 1897. Transformers are still used today to step up voltage as electricity enters the transmission system and step it back down when it reaches a distribution node. Despite Edison's best attempts to discredit the AC technology, including using high-voltage AC power to brutally electrocute an elephant at a public demonstration, Tesla won, as you can see by stepping outside and looking at a transformer on nearly every utility pole in the world. But now DC transmission is back, not as a competitor to the AC system, but as a supplement. A series of technology breakthroughs in the 20th century, including mercury arc valves, thyristors, and insulated gate bipolar transistors, effectuated easy conversion between high voltage AC and high voltage DC power. This opened up the use of DC transmission for the movement of bulk power over long distances. As you can see in the drawing from Hartley, a DC line can move the same amount of power with substantially less wire and infrastructure than an AC system, and so has the potential for significant cost reductions. DC lines are also a superior technology for underwater power cables. This is because a buried AC cable of sufficient distance can produce so much reactive power as to fill up the entire cable capacity, resulting in no usable transmission. DC cables, by comparison, do not create reactive power. DC interlinkages can also provide benefits to the existing AC power system. They allow power transmission between unsynchronized AC grids or even between AC grids running at different frequencies, which can increase system operator access to additional resources in an emergency. And in the event of a catastrophic failure on one AC grid, the DC line isolates the problem and does not allow interference with the other system. For our purposes, we are mostly interested in the potential of HVDC for the transmission of energy from remote, high-capacity renewable energy resources. But there are challenges to HVDC uses. HVDC requires a relatively strong and stable AC system on both sides. It can also create harmonic distortions in AC systems and has limited control of the reactive power interchange with the AC system. Voltage source converter, or VSC HVDC technology, aims to address these problems by giving transmission systems themselves more control over voltage at AC to DC links. Alstom, for example, has designed a VSC technology that combines converter cells that can shape voltage waves with high numbers of switches to direct the converter cell activities toward the DC or AC system. Manufacturers claim that such VSC systems can operate in conjunction with weak AC systems, providing advantages for offshore wind transmission. That's because the voltage source converter can control both real and especially reactive power flow in the AC system by controlling output voltage. The idea of a collection of high-voltage DC and AC transmission lines working together across continents and power grid systems is called a supergrid. The concept has gotten the most attention in Europe and Northern Africa, where a combination of offshore wind and desert-concentrating solar power promises the dream of a renewably powered continent. Such systems both connect disparate AC grids to strengthen capabilities and allow for movement of renewable power across time zones to match generation and load. HVDC is a critical component of supergrid plans because of the vast distances involved, as well as the need for multi-terminal systems that can independently balance output from an entire region's worth of wind farms prior to interaction with an individual AC grid. It is perhaps appropriate that our final slide for the Renewable Energy Technology module is one of the oldest. This is Buckminster Fuller's vision of a global electricity grid, copyright 1938. For Fuller, a futurist and visionary whose ideas would be considered outlandish, to say the least, by the people who manage and operate our current energy systems, a global grid was a triangulated solution to pollution, poverty, and war. By integrating daytime and nighttime parts of the globe into a single system, individual wind and solar plant variability become essentially non-issues for integration purposes. And by extending the reach of the grid to every corner of the populated world, all countries would have access to clean energy at a shared cost. Fuller saw political ramifications to the system as well. Asked by a 12-year-old boy how he would solve international violence problems, he answered, "I always try to solve problems by some artifact, some tool or invention that makes what people are doing obsolete, so that it makes this particular kind of problem no longer relevant. My answer would be to develop a world energy grid, an electric grid where everybody is on the same grid. All of a sudden there would be no problems anymore, no international troubles. Our new economic basis wouldn't be gold or dollars, it would be kilowatt hours." Fuller did not live to see his vision become a reality. But is such a thing possible? Cost-effective? Likely in a world divided into 192 countries? Perhaps yes, and perhaps not. But isn't it worth asking? This is the end of the APEC Renewable Energy course module on renewable energy technology. We hope you have enjoyed the content and learned something in the process. I'm Adam Reed from the Renewable and Sustainable Energy Institute in Boulder, Colorado, USA, Earth. Thank you for your attention.